Oh, you wanted to know the formula for holy water? H2OMG. Anyway, tough week. Anyway, go over homework. Balancing half reactions 4 through 8. I'm going to give you the first two, and then I will post the rest of them. Reactivity series. Objective reactivity series today. Redox reactivity table J that's in the packet. It looks like a lot, but the last 4 or 5 are just multiple choice. And a reminder that Spiral 16 is due on Monday. Okay, you will have had it for 2 weekends. Okay, so let's take a look at the homework. You had 4 through 8. I'll do the first 2, and then we'll go from there. Okay, anything by itself is 0, 0. Anything monatomic ion is its same charge. Aluminum, 0. Goes to a positive 3. It does that by losing electrons. You can see how many at this point. Aluminum, 0 on this side, reactants, 3, negative 3, 0. So it's losing electrons, it gets oxidized, making it the reducing agent. Copper, 2+. It gains electrons to become copper solid. Now this is going to become more important because, as we just saw with the electroplating thing, that solid is going to start forming on the other metal just like we would do in electroplating. So that's done by 2 electrons. Copper is reduced, and it's the oxidizing agent, therefore. Now this is the first time we've come across this where the electrons are not the same. So if they are not the same, we have to multiply by something to get them to be the same number of electrons. When we do that, we have to multiply everything inside there. So if you got messed up on this one, don't worry about it, but this is how you do it. So if I've got a 3 here and a 2 here, the easiest thing would be to multiply everything here by 2 and multiply everything here by 3. So I would end up having, like this, 2 aluminums. I'll do it in halves still. 2 aluminum 3+. 3 times 2 is 6. Switch colors. 3 coppers. Whoops, that's a big C. 3 times 2 is 6 electrons. 3 times copper. Now I can do the total. 6 and 6. Oh, I didn't want that, I want this. 6 electrons, I can cross those out, and then I can total it. So 2 aluminums plus 3 coppers yields 2 aluminums plus 3 coppers. 2 aluminums, 2 aluminums, 3 coppers, 3 coppers. 0 plus 3 times 2 is 6, positive 6 over here. 2 times positive 3 is 6, plus 0, positive 6 over here. Now I'm done. Okay? How about number 5? Then I'll post the rest of these. All right, zinc. Oops. 0. 0 plus 2 plus 2. This is going to be straightforward. You can see that the number of electrons is going to be the same again. Zinc 2+, 2 electrons, yes? That gets oxidized. Zinc is oxidized, making it the reducing agent. Tin 2+, it's going to gain 2 electrons to form tin solid at a 0. Two electrons, zinc 0 plus tin plus 2 yields zinc plus 2 plus tin 0. 1 zinc, 1 zinc, 1 tin, 1 tin. Positive 2 plus 0 is positive 2. Positive 2 plus 0 is positive 2. We're done. Okay? I'll post the other 3. Oh, what's getting oxidized here? Must be the tin. And if it's getting, it's getting reduced, making it the oxidizing agent. All right, let's take a look at the this part here, which is the activity series. All right, it's a 4-minute video. So let's take a look at that. Making predictions using the reactivity series.
Metals can vary greatly from one another in terms of their appearance, properties, uses, and reactivity. Gold, as an example, is yellow, relatively hard, and very unreactive. Potassium, on the other hand, is gray, relatively soft, and reacts vigorously with oxygen and water. We can actually organize these metals according to their reactivity. This arrangement is known as the reactivity series. The most reactive metals are at the top, and the least reactive at the bottom. We can use this series to predict whether or not a single displacement reaction will occur. This is often of importance in industry as it can be used to obtain pure forms of valuable metals from their compounds. A single displacement reaction is a reaction whereby one element displaces another within a compound. The key idea here is that a certain element can only displace another in a compound if it is more reactive. Here is an example. When we add a strip of zinc to an aqueous solution of copper 2 sulfate, we can see from the reactivity series that zinc is more reactive than copper and can therefore displace copper in copper 2 sulfate. We can see this happening over time. The bright blue copper 2 sulfate solution gradually turns into colorless zinc sulfate, and copper metal begins to deposit on the zinc strip. Can you predict the products from this single displacement reaction? Pause the lesson and continue when ready. As copper is more reactive than silver, it can displace silver in silver nitrate, producing silver metal and aqueous copper 2 nitrate. If you look closely at the series, you will see that hydrogen and carbon are added for comparison purposes. This is important to help predict whether or not a metal will react with an acid or if it can be extracted from another compound. Magnesium metal will dissolve in hydrochloric acid, releasing hydrogen gas and forming aqueous magnesium chloride. Since platinum is lower than hydrogen on the series, it will be unreactive in hydrochloric acid. This series is also important when it comes to the extraction of metals from their ores. Malachite contains a high percentage of copper 2 carbonate. Heating copper 2 carbonate decomposes it to copper 2 oxide. When you add charcoal, a form of carbon, this enables the extraction of copper metal, as the series tells us that it is more reactive than copper. Can you predict the products of this reaction? Pause the lesson and continue when ready. Here is the answer. In summary, the reactivity series ranks metals according to their reactivity and can be used to predict whether or not a reaction will happen.
Okay, now you've got this in table J, which is right here. Now we have looked at this before. We were comparing, I wanted you to figure out whether one metal could displace another. And if I added an acid, would the acid cause hydrogen gas to be liberated or given off? Okay, so in order from top to bottom, these are most reactive down to the least reactive. And what that means is oxidation is up here and then it continues down here. So if I have lithium and calcium together, if I mix them together, the lithium would get oxidized and the calcium would get reduced. If I had strontium and aluminum, strontium would get oxidized, aluminum gets reduced. So let's take a look. Okay, it's used to predict whether two metals will spontaneously react. That's an A, spontaneously react with each other. Metals on the top of the list are more likely to get oxidized and therefore are considered more active. So for example, if you have a magnesium strip in a solution of copper ions. Okay, let's take a look. Actually, I've got zinc here. This is a strip of zinc. This is copper sulfate. If I put zinc in copper sulfate, will zinc displace the copper? Let's look at our series. Whoops. Zinc is here. Copper is down here, pretty unreactive. So zinc will oxidize and lose electrons, causing the copper to get reduced. So there will be reaction. Look at that. It's already happened. It didn't take long at all. So if I leave that on there, let's see what's going to happen. So they used zinc or magnesium. I used zinc. Magnesium metal will become oxidized and form ions. So it's losing electrons. The copper ions will get reduced. Remember, reduced means that they're going to be gaining electrons. So they gain electrons to become copper, and they come out of solution and form on the strip. So what you're seeing here is, I can get it. You can kind of see, I can see it, it's a little hard for you to see, but this is a little bit of a reddish color because copper has a red color, like a penny, reddish color. So if I leave this in here long enough, it will draw off the copper that's in the solution. So this is aqueous. It's picking up the electrons from the zinc, and I could do a full balanced reaction with this. Actually, let's do that. So if I start with zinc and I add it to copper ions, I'm going to have, this is 0, this is zinc 0. I'm going to have zinc 2+ and copper metal 0. Okay, so if I split this up, I can have zinc losing electrons to form +2 electrons, and copper ions gaining those 2 electrons from the zinc and forming copper solid. So the copper solid is what is forming on the strip. the zinc is getting covered with the copper. What's going to happen is eventually this blue color is going to get faded. It will get faded because these are copper ions that are going to go from the solution and then form on the strip. And as it does that, it's going to become more and more pale. Eventually it'll just settle on the bottom. Okay? However, since copper is less active than magnesium, if one were to put copper strip into a magnesium solution, nothing would happen. Okay? Let's go back to the CRT. So, if I put silver, a strip of silver in copper solution, nothing would happen. Gold, same thing. That's why gold is so one of the reasons why it's so valuable. It doesn't tarnish because it's so unreactive. If I put tin inside cobalt sulfate, nothing would happen. Hydrogen is used as the standard, just as you saw. If a metal is more active than hydrogen, it will replace it when exposed to it, such as an acid, and then you can predict. 3 examples. I'm not going to go back to the list, but these are there. Pretty straightforward. All you have to do is look at Table J. All right? Tomorrow we will look at the second kind of voltaic cell, electrochemical cell, the different kind of cell, and then we are close to done with this unit. Okay, so we're looking at a test probably on somewhere around Wednesday, maybe Thursday. All right? Reminder that spiral number 16 is due on Monday, and the reactivity table is your homework for the weekend. Let's see, wrong folder. Let's see if I can find it. I'll post it, of course, but it's in your packet. Okay, I'll have to post it because I can't see it right here. All right, see you then.